One up.
People find beauty in patterns. Patterns in nature, in architecture, and in mathematics. Designer Jane Barnes combines her love of patterns, math, and clothing to create high-end menswear. The common thread running through her work? Mathematical sequences. A sequence is an ordered set of things or events. Here, the sequence 5, 21, 85, 341 represents the number of crossing points where the vertical and horizontal lines intersect. Jane Barnes takes this relatively simple sequence and spins it into something complex. Each element in a sequence is a term. The terms of a sequence follow a pattern, which is described by a rule. Typically, the rule tells you how to derive a term from the preceding term. Consider the sequence reflected in the patterns used by designer Jane Barnes. The rule is times 4 plus 1. Each term is one more than 4 times the term before it. If you can decipher the pattern and determine what the rule is, you can figure out the value of any term, whether your sequence has 4 terms, many more, or is infinite. You can add terms in a sequence to get a series. For example, the series associated with this sequence is the sum of its terms, 5 plus 21 plus 85 plus 341, which equals 452. The terms of the sequence are also the terms of the series. Let's look beyond the New York fashion scene for other examples of sequences and series. Just outside Denver, in the foothills of the Rocky Mountains, is Red Rocks Park. Iron in the soil gives the rock formations their color. One of the park's big attractions, Red Rocks Amphitheater. It's a spectacular venue for musical concerts and attracts top-notch artists and capacity crowds. Let's say there are 86 enthusiastic fans in the first row, 88 in row 2, 90 in row 3, and in row 4, 92. The first 20 rows follow that pattern. It's an example of a mathematical sequence, an ordered list of numbers. Each element is a term in the sequence. In this case, the simple rule that governs the sequence is easy to see. Each term is 2 more than the previous term. This is an arithmetic sequence because the difference between any term and the term before it is constant. It's called the common difference. We can determine a general formula for the value of any term in the Red Rock sequence, that is, the number of seats in any of the first 20 rows. Let's say n represents the term number, its position in the sequence, and a sub n is the value of the term. The first term, term 1, has a value of 86. Term 2 is 86 plus 2. Term 3 is 86 plus 2 plus 2, or 86 plus 2 times 2. In other words, the value of each term is the sum of 86 plus 2 times 1 less than the term number. A sub n is equal to 86 plus 2 times n minus 1. Let's suppose that for publicity purposes, a Denver radio station announces a contest. The first caller to correctly state the number of seats in all of the first 20 rows at Red Rocks will win tickets to a weekend concert. But you don't have to guess. You can figure out the value of each term, the number of seats in each row, and add. The sum of the terms of a sequence forms a series. The series is often written in summation notation, also known as sigma notation. The Greek letter sigma is used as the summation symbol. Since this series is the sum of the terms of an arithmetic sequence, it's an arithmetic series. To write the sum of the first 20 terms of the Red Rock sequence in summation notation, start with sigma. Beneath it, define the index of the first term of the sequence to be used in the sum, n equals 1. Above it is the index of the last term, 20. To the right of sigma is the formula for the sequence, 86 plus 2 times n minus 1. This summation notation tells us to add all of the following: 86 plus 2 times 0, 86 plus 2 times 1, 86 plus 2 times 2, all the way to 86 plus 2 times 19, for a total of 2,100 seats. The value of the series is 2,100. Those rows can hold quite a series of music fans. An American woman, Shelley, is married to a Moroccan-born man. They throw a traditional Moroccan party to celebrate the birth of their first child. Guests wish them long life, good health, and happiness. Let's imagine for a moment that we can see what the future will bring for this family. Suppose that Shelley will have 2 children, and so will each of her descendants. How many descendants will Shelley have 20 generations from now? Start with Shelley. Let's call her Generation 0. She has 2 children, the first generation. Shelley's children have 2 kids each, so there are 4 members in the second generation. Each of the 4 of them also has 2 offspring, so Generation 3 is a party of 8, and so on. 1, 2, 4, 8, these numbers form a clear pattern. Each successive number is double the one before it. This is a geometric sequence in which the ratio of any term to the previous term is constant. In this case, the common ratio is 2. Of course, no family is likely to grow at such a predictable and constant rate for a long time. But in our peer into the future fantasy projection, Shelley will have 8 great-grandchildren. How many descendants would be in Generation 20? We can write a general formula to find the value of any term in the sequence. Let n represent the term index number for its position in the sequence, and a sub n is the value of that term. Generation 0 has just one person, Shelley, so term 0 is 1. Term 1 has a value of 1, representing Shelley, times 2, the number of children she has. Likewise, term 2 is 1 for Shelley, times 2 for Shelley's children, times 2 for their children, and so on. In short, the term number n is the same as the number of 2's being multiplied. So the general formula for this sequence is a sub n, the value of term n, equals 2 to the nth power. Generation 20 will have 2 to the 20th members, more than 1 million people. Now, what if we wanted the total number of people for Shelley plus all her descendants through Generation 20? That would mean adding up all the terms for that part of the sequence. The sum of the terms of a sequence forms a series. Here's the summation notation for that series. It tells us to add 2 to the 0 power plus 2 to the first power plus 2 squared all the way through 2 to the 20th power, or 2,097,151 people. That's Shelley and her descendants through the 20th generation. And to think, it all begins with one woman, and of course, her husband. In many families, parents plan to pass on an inheritance to their children, maybe a home, some money, an investment. But let's imagine a fictional family, the Steeles, in which a job is passed from one generation to the next, a job in the scrap metal yard. Suppose the first Steele to work there will earn a starting salary of $50,000 a year, but has to make a choice that will affect all future generations. How will the salaries of all those Steeles change from year to year? Option number 1. After just his first year, Mr. Steele will get a raise of $100,000. That's great. After year 2, his raise will be $80,000, or 80% of the previous year's raise. Sounds not quite as great. Each year, his raise will be 80% of the previous one, or, put another way, 20% less than the year before. This is a geometric sequence, since there is a constant ratio between terms. The ratio is 0.8. Look at what this does to Mr. Steele's raises. His salary increase after year 5 is about $41,000, nearly 60% less than his year 1 increase. And after 10 years, it's less than $14,000. His salary grows by a smaller and smaller amount. There's something interesting about this sequence. It is theoretically infinite. The Steele family's annual raise can be cut by 20% an endless number of times. But the more that happens, the closer to 0 it gets. That would be true for any ratio less than 1. The series for this sequence, the sum of the increases for all the Steeles over the years, converges to a limit. Even with an infinite number of terms, the value of the series, the total of all the raises, will never exceed $500,000. Add that to the starting salary of $50,000, and you see the highest possible salary will never exceed $550,000. That's not a bad salary by today's standards. But let's look at option 2. Mr. Steele will get a raise of $100 after his first year on the job. Pretty meager, but every year the raise will increase by 10%. As in option number 1, this is a geometric sequence because each term is a multiple of the previous term. But this time the ratio is greater than 1, 1.1. So the Steele family's raises will increase faster and faster. After year 2, Mr. Steele will earn $110 more than the year before. The next year, it'll be $121 more. And the year after that, $133. It'll take 26 years for Mr. Steele's annual raise to exceed the $1,000 level. This doesn't seem like the Steele family's best option, and it isn't in the short term. But look at what happens after 74 years. The annual raise for option 1 is less than a penny, but for option 2, it is greater than $100,000 and increasing without limit. And if you look at the series for each of those options, the sum of all the raises, what you find is this. At year 66, the series for option 2 surpasses that for option 1, and each subsequent year the gap widens. Any ratio greater than 1 will yield an accelerating, diverging increase. So if Mr. Steele is looking for long-term gain for his family, the better option is number 2. Oops, he better take it before the boss changes his mind.